Welcome to Talk Universe. We've got an interesting subject today. I'm not afraid of controversy. Let's talk about climate. This is one of those subjects that people get really upset about. We're wrecking the world. We need to take great measures to fix it. Let's look at the facts. Most people can't tell you how much of the atmosphere is carbon dioxide. That's a very important factor. So let's have a look at that. Let's have a look at the data. What's the difference between climate and weather? Now, climate is the long-term set of conditions. And so in a given area, you will have certain rainy seasons, snowy periods, average temperatures, and those can last for decades or centuries. That's climate. It's the standard local conditions. Climate's typically stable over many lifetimes. Weather, on the other hand, is short-term and it changes all the time. And so a few hours or days can pass. You'll have rainstorms and sun, a little snow, a little wind, whatever. But weather is changeable and can vary very greatly. Now, let's talk about how this all starts. In the beginning, we had a pretty uncomfortable place here. Well, we weren't around. Molten planets formed from the stuff out in space, gas and dust and clouds. And after a while, those planets settle down and they have their first atmospheres. Now, what would the atmosphere on a new world look like? Something that's only a few thousand years old, perhaps. The first atmosphere was a gas from the molten lava venting away and surrounding that new planet. So this planet's a ball of lava out in space. And the conditions are pretty oppressive. 700 to 1200 degrees centigrade, that is definitely molten material. Air pressure, 1 bar, barometric pressure, 1 atmosphere. We had about 250 to 300 bars of pressure on our planet. Venus has a remnant of that with about 90 bars of atmosphere. And the atmosphere was made not of oxygen, not of nitrogen. It was made of carbon dioxide, ammonia, methane, water vapor, hydrogen, nitrogen, and sulfur compounds from all the volcanic activity. Not breathable, not fun. And we'll get to the cycles in nature. Sorry. How climate develops and changes over time. Lighter terrain and darker terrain can absorb or reflect the heat from the sun. And we tend to see that bodies of water stabilize temperatures like heat batteries. So oceans and lakes warm up and they spread that heat in cooler periods, or they're cooler than the hotter area and they help cool it down. And ice sheets tend to remain cold by reflecting. So if an area gets snow, the snow reflects the sunlight back and that keeps the heating down. Ice sheets are self-perpetuating. Lava fields and rocky areas can have huge swings of temperature. They get very hot in the daytime, but then they drop it away and get cold at night. Vegetation here is the key. Now, vegetation is very different because it creates its own local climate through the use of water. Plants grow, they shield the ground from heat, and they emit water vapor that evaporates into the atmosphere. The plants have a process known as transpiration, the passage of water through the plant and out into the atmosphere again. So cycles in nature, this is very, very important. You'll see this is an ice-covered planet. Let's say you had a time machine and you could travel 50,000 miles away from the Earth and look down on the planet. And we're going to go back in time, one day at a time for 1,000,000 years, and we're going to take a picture of the Earth every day. If we were to put that together into a video and run it, let's say, 60 frames per second, like any good RPG or decent video, you would have 1,000,000 times 365 and a quarter days, or let's call it 365,242,000 frames of video. If you were to stick that together and play it at 60 frames per second when you were done, you'd see a video that would last about 40 days, 41 days. Now, you'd see something very interesting. Most of the time on that video, our planet would be covered with ice, and only about 40 to 50% of the time would it be not icy, not glacial cover. Why is this? And you notice another thing. As you're playing this video back about twice a day, you would see the ice come and go, and then come and go. And so overall in 1,000,000 years, you'd have about 90 ice ages. Let's see why. So sunspots, believe it or not, affect our climate. There's an 11-year cycle to sunspots, and when the sunspots are erupting like mad, they're actually heating our planet slightly because heat from the sun is being transferred into its corona and eventually to the top of our atmosphere, to our planet. In periods of time when the sunspots are low or absent, like in the minimum of each sunspot cycle, the temperatures of our planet go down. And we had a large cycle. There's two cycles here. There's the 11-year sun cycle, and there's about a 400-year cycle buried in that. And one of them passed away between 1600 and 1750, was called the Maunder Minimum, and they called it the Little Ice Age. During that period, the solar activity dropped to zero, basically no sunspots. And what happened was crops failed, ice showed up, winters were tough. So we had about a 400-year period just back from 1600 to 1750, this 400-year cycle, that showed up for about a century and a half, and it caused crop failures and drops in population, and the world was much colder. This Maunder Minimum is a little ice age right in the middle. Why did it happen? I'm getting ahead of things here. So we have a couple of things called Milankovitch cycles, different types. One thing is our orbit is not a perfect circle, it's an ellipse, and the eccentricity is how elliptical it is, and it changes over a period of about 100,000 years. Okay, we have obliquity, and that's the orbit's angle, the orbit of the angle from the ecliptic, the plane the planets are in, and that changes over time of about 41,000 years. So we got a couple of changes in our orbit that can change how much sunlight we get. Then we have precession. If you watch a top spinning down, the axis of the top wobbles, and there are two wobbles built into one that the Earth goes through. The big one is called precession, and it lasts about 26,000 years. And then there's a tiny one that wobbles a little around the axis as it's spinning down, and that's a 21,000-year cycle. So we put all these things together, and we plot out the change in sunlight, and we get a picture of how these things are changing. The first curve you see is the eccentricity of the orbit, and you can see that the sunlight levels are going up and down. The second is the change in the tilt as precession occurs. It's a shorter period, and you can see all the bumps at this red graph in the middle. The precession of the pole as it changes, you can see another cycle here. When you put all of these cycles together, a strange thing emerges. And here it is. This is the cycle of ice ages. Now, as I mentioned, for most of the history of our planet, we see it in ice if we were to travel back in time and take a photograph all the time or just look at the planet. The yellow portions are when it was warm and clement and things were very, comfortable for people. These periods in here below the line are when the planet was in an ice age. Where are we? See this little red arrow? You are here. This little window is the last 6,000 to 8,000 years of human history. And in that period of time, that's when things warmed up. Humanity was able to come out of the holes in the ground and develop technology and really grow as we see our world today. Previous to that, and this was 11,700 years ago, we had an ice age that ended, and it led to our civilization being able to have these capabilities. So all of this time below the line, the Earth is in ice, and the yellow periods, it's thawed out. These are cycles that are built into the nature, the orbit of our planet, the movement of our planet. We have nothing to do with. We often hear that the CO2 has grown to the point in our atmosphere where it's damaging the climate. Let's look at that. Nitrogen makes 78.08% of your air. Right here, that's nitrogen. Oxygen, the green wedge, is 20.95%, a little less than 21%. That little wedge in there, the pink one, is argon. Argon is inert. It doesn't chemically react with anything, really. And if you're a welder, you would know what argon is. It's an inert gas used in the welding process quite often. Carbon dioxide. You can't even see it on the graph. Out of all of these gases, carbon dioxide is 0.04% or less. There is about 2,800 times more gas in the atmosphere than CO2. CO2 is one of the tiniest components. So where does it come from? This tiny fraction of CO2 seems to have a massive effect on the temperature. Let's see about that. When we look at the sources and sinks for CO2, we discover that our contribution out of the 800 parts in the atmosphere comes down to about 9. And the 800 parts in the atmosphere are taken up some by photosynthesis and by soil carbon being absorbed. The ground takes up some units. Microbes send some out and take some in. Oceans do a lot of air exchange. They take a lot of that CO2, like 90 units compared to our 9. And some of it goes down to sink in the sediments under the ocean. Overall, when you add up nature's contributions and usage and ours, nature makes about 95% of the CO2 in the atmosphere and the environment. All of our industries combined, everything mankind is doing, is estimated to reduce about 3.7 to 5% of the global CO2 emissions. That's it. So we're 1 part out of 20 at the worst. Termites are estimated to produce 5% of the global carbon dioxide emissions. That's as much as everything we do. One volcanic eruption can produce more CO2 in a week than humanity does in a year. So what is our effect? What are we doing that could affect our planet? Our greatest effects are actually in a small number of areas, and it isn't climate. Sewage and wastewater discharge is one of our biggest ones. We fail to process sewage and wastewater, and it ends up getting discharged in lakes, oceans, and streams. Landfills, leakage into the groundwater, ocean harvesting without remedies. If you had a garden and you picked it all the time, you harvested it all the time, but you never replanted, you never fertilized, you never watered and cleaned it, that garden would not survive. We're doing that to the oceans. Fracking, destroying the groundwater barriers. Pharmaceuticals being released into the waste. They are compounds that do not metabolize in most organisms, plants, animals, or anything. So they simply build up, and eventually they reach a concentration. Remember, every molecule is a message to a cell, and we don't know what those messages combined are making them do. We're failing to plant trees in wild areas. We've been collecting money, I say the governments, have been collecting money for ages to fight global climate change. And they've taken a couple $1 trillion at least, but they haven't planted, as far as I can tell, a single tree anywhere. Where are the trees they said they were going to plant? They don't exist. In fact, satellites show that the planet is greening. Well, there's a reason for that. CO2 in the air feeds plants. That's plant food. And if you take it out of the air, you reach a point where it's like 0.3, maybe it's okay, 0.2, the plants die. We can't do that. What really affects our climate is nature. We don't have a handle on it at all. But what we are doing is poisoning the planet. So we have materials going into the groundwater, into the environment, things that should never be there. I know people complain a lot about plastic. Oh, it's going to last 1 billion years in landfill. No, it will not. Let me tell you something. If plastic were that durable, we'd be roofing our houses with it, and it doesn't happen. Sunlight destroys plastic, and that's a rule. It's very simple. It's not the durable material you think it is. There are microbes that eat plastic, and we actually have remedies that can take waste plastic and convert it back into fuel or into detergents or into soaps or other compounds. So we know how to fix all these problems. We actually have technology in hand that very easily can fix all these problems, but we're not doing it. I'll talk about that in another podcast. But basically, in summary, I want to say we are not changing the climate of this planet. And by the way, I want you to buy A Fossil Hunter's Guide to Mars, the book edition 2, which I just finished publishing. I think you're going to find some amazing things about the albedo of Mars, how much energy it gets, how much life it supported, the fossils that are there, and why is it that NASA isn't admitting that it's happened. Buy the book, A Fossil Hunter's Guide to Mars. Go to my site, schultzlaboratories.com, and right on the front page, you'll find a link. I'll post it also under the video here. Help support what we're doing. We're trying to get the word out about this. We know how to fix what's wrong with the world, but we're not doing it. Let's take steps to fix the world. make the world a better place. And have a great day. Thank you.